Hello, everyone. Welcome to the Nomads Podcast. I'm your co host, Bhavya.
And I'm your co host, Prachi.
One of the great advantages of being a physicist in Texas is that you're genuinely surrounded by incredible physicists across the Houston, Austin, Dallas, and College Station area. The summers here are, of course, hot, but what better way to spend an afternoon than talking to a fellow physicist? Last time we were at Rice University, and this time we're at Texas A&M University. Today we're talking to Professor Shenglong Xu, who's a theoretical physicist working on quantum many-body dynamics, quantum chaos, quantum information, and algorithms for quantum simulation. His research explores how large collections of quantum particles evolve, scramble information, and generate entanglement, and sometimes behave in surprising ways that challenge our usual intuition. In the episode, we also talk about the growing role of AI in science and how new computational tools might help physicists understand systems that are far too complex to solve by hand. So, if you're interested in these fundamental concepts of theoretical physics that also inform near term technological revolutions, you're in for a treat. So, let's go. Shenglong Xu, welcome to the Nomads Podcast.
All right, thanks for having me here.
Yeah. So I know you have like a very broad range of interests, starting from many body systems, quantum dynamics, quantum algorithms for classical and quantum simulation. Now, I find all of these particularly interesting, not because it is also my active area of research, but all these areas of physics have some deep and meaningful connections to near-term technological revolutions. So they're also kind of tangible compared to many other fields of physics. So again, that adds on to why this area is very interesting. So let's unpack these one by one.
Okay.
Okay, let's start from the beginning. What are quantum many-body systems? Why are people interested in it? And also, when people talk about many-body systems, they say something like, they have emergent properties. Tell us, what does that mean, and why are these systems very interesting when they're out of equilibrium?
Okay. Yeah, sounds good. So many body physics means that you have tons of individuals together. They do something together. It's like we call it collective behavior.
Mm-hmm.
So which means that each of the particle or each of the individual may have their own sort of rules, but then when they together, they have sort of new rules can be formed. I mean, an example I usually use, for general public is that let's say you have some birds flocking. Okay,
Mm-hmm.
we have a lot of birds here. So they form, and when they watch them, they form different patterns in the for flocking. But those birds, single bird in a flock, they sort of have some sort of local rules. They follow the other birds. So these questions is how those local rules lead to those global patterns. That we call it's called like an emergent phenomenon. It's basically how sort of a global sort of pattern come out of those local rules.
Mm-hmm.
And in physics, or in particular, I don't study birds. So in my field, we study the or the individual. The subject is sort of microscopic particles, like qubit in quantum computers, electrons in solids, atoms in called atom systems. Those are our individual, the sort of the building block of the many body systems. They talk to their friend through some rules that can be defined by some Hamiltonian. And we ask, what is the sort of global pattern they can have?
I see.
Yeah, I mean, for example, so it's like birds, the bird flocking patterns in solids. They can the electrons. They can have different orders, like magnetism, superconductivities, With some material is metal, some material is insulator. But they all come out from those same single. I mean, from the same, like, what's the word I'm talking about? Like the same individuals.
Right.
Yeah.
Right. Right.
So, understanding this a little more,
Yeah.
when we start learning about quantum mechanics,
Yeah.
most of us start with a single quantum object, like
Correct.
a
Yes.
electron in an atom or a harmonic oscillator.
Right.
What exactly changes when we go from one quantum system to many quantum systems interacting with each other?
Yeah, so right. So when we start the quantum mechanics, I don't know how you learn quantum mechanics. The way I teach it, I always start with qubit or two level systems. You know, spin up and spin down, and talk about what kind of quantum mechanics can do to change the state.
Right.
So simple and straightforward. So it's two-by-two matrix or two-dimensional vector. But now let's say if you put a lot of them together. So first of all, it becomes more difficult to track all of them because there's this jargon called the curse of dimensionality. Basically means that if you have n qubits or n two-level system together, they have 2 to the n.
Dimension
But
Hilbert space.
yeah, the dimension of Hilbert space. And also, but it's not a random 2 to n times 2 to n matrix. It has some sort of locality built in there because for example, each qubit can talk to its neighbors, but maybe not the arbitrary far away qubits. Or each atoms or each electrons talk to its neighbors. So there's some sort of locality built in there. It's not arbitrary. And so the question is say, now what can we understand regarding this general 2 to the n qubit system or 2 to the n many body systems? Or I guess the question is sort of, but what do you mean by understanding it? Because understanding the wave function itself is a 2 to n dimensional vector. That's impossible. It's just too much information there. So we need some sort of more like a macroscopic sort of properties we can use to sort of describe it.
Right.
What's it? Some people use its ordering. Whether if it's all, for example, if it's all spin up or spin down or it's random, it's usually to the magnetic order. There's some different order parameters to sort of describe a macroscopic phase of matter.
Right.
And that's what people have been studying condensed matter for a long time. Like, you have given a Hamiltonian describes, you have n particles or n spins. The Hamiltonian describes their interactions, some local interactions. And people ask, what's the ground state properties? Means that if you cool down the system to really low temperature, what are the global property of the state? Or people ask, what's the finite temperature equilibrium properties? Which means that, you have some statistical ensemble, like at some finite temperature, the system connected to some heat reservoir. And then you ask, what's the property of that Gibbs ensemble? And now, more recently, people start to think about, what is the non-equilibrium properties of those systems? Means that, because for ground state, for equilibrium, means that if it sits there static. You do not have the time dimension. But one can also do, now in those quantum simulators, they can sort of start with a arbitrary state you can prepare in a lab. Which is not in equilibrium, means that if you start it, the system is going to evolve in time.
Right.
And the question is, how that state evolving in time? Are there sort of universal phenomena there? Can we describe? So now we're not only looking at a particular time slice. We're trying to understand this dynamical process. Yeah.
Right.
Yeah.
Right.
So that's very fascinating about the dynamics of these quantum many body systems, because we can learn about quantum matter in real time. So what are different ways that we can probe the dynamics of quantum many body system?
Yeah, that's okay. Very good. There's a few ways people usually use to sort of understand. The simple, I guess the simplest approach is something from a quantum state. One can do some local measurement, like measure like a local observables. Whether at this particular site, if it's spinning up, spinning down, or what is the density of the state at the particular location. And you can say, let's say we start with something that we put start with a state that we put all the particles on the left hand side of the box,
Mm-hmm.
which of course is not equilibrium because there's no reason all the particles start to the left in the box.
Right.
I mean, it's kind of like if you open a bottle of perfume in the room, the perfume is still in the bottle at the beginning, but it still start to diffuse.
Right,
So
right.
it's kind of similar. So in quantum system, you can sort of measure how the particle diffuse over time, or how spin orientation change over time. Those are called local observables.
Right.
And there's also a very sort of fascinating topic called thermalization. It means that through sort of the talking to everybody else in the box, the system will start with some non-equilibrium phenomena, but after some time it will sort of goes to some equilibrium state.
Right.
Yeah.
So that's all of these are great topics. We have a lot of questions about them, but let's again slowly unpack. So you briefly mentioned this word. When people usually talk about quantum dynamics, they always talk about this word called information.
Okay.
Now, information it has a lot of different meanings.
Correct.
Tell us, our viewers, how you think about what information is, and what is the lack of information, what is information, and how particularly you think about it. What seems to you the most intuitive definition of information?
Yeah, right. Okay, yeah, this is a great question because this is, the word information can be vague.
Yes.
So from my view, okay, what do you mean by information? So, let's make this simple first. Let's say our system is closed. Means that the system is closed, not talking to the environment, and all the information contained in the systems. Okay, then what do I mean by information here? Then what we need, so in that case, the system is described at the time is described by its wave function.
Mm-hmm.
So no matter whatever information we mean, it means it's a wave function itself.
Right.
Let's say it's to be more specific. It's let's say consider n qubit systems. I always use qubit because it's kind of easy to sort of understand. It's
Right.
it's just n2 level systems, but it can be anything else. It can be electrons, can be whatever. But let's just use qubits. So it's 2 to the n. So it's all the information in that vector. But now the question is, okay, so that is a lot, but what people can measure, because in principle one can measure the 2 to the n, wave function amplitude, but it's not very, very practical, because for n equals 100, which people can now simulate in a quantum simulator, it's like 2 to the 100 is like gigantic number.
Yeah.
So okay, what do we mean by information here? Some people means that okay, they measure their local, as I said, local observables, local density or local spin orientations.
Right.
In that way, so let's say if you measure sigma z, which means spin up, spin down at every site,
Right.
you get n numbers. So that n is coming from the 2 to the n numbers, but it's some information that we can understand.
I see.
Right? So that's one thing. But though some people, using information more like, it's like quantum information. It has some somewhat different meanings. Okay, the way I usually use it is like imagine. Let's say you have quantum state, and but let's say we have a qubit that so let's say everybody else in some non-state, let's say spin up or zero state, and there's one particular qubit we have. It's like in a particular, we encoded in some particular state, alpha 0 and beta 1. So now the information for that qubit is small. It's it just a two-dimensional vector.
Right.
Alpha and beta. Let's say it's our information. Or you can imagine generalize it to a small set of the total n qubits. You can encode some information that you want in that small set. That can was the more sort of rigorous. I don't know what if it's more rigorous, but it's a way to sort of define information there. And then you can ask a question. Okay, then now of course this initial encoded state is not a equilibrium state. So when you turn on the time evolution, they're gonna evolve in time. And you can ask a question. Okay, where you can find that two-level system information among the involved state. Because now we have this situation, right? So our four-way function is 2 to the n.
Right.
Our the information we just encoded is two numbers. So how do we where that the two number is hidden in that the 2 to the n gigantic numbers? Okay, because so at time 0. Well, that information is just located in the first qubit that you can just measure and get the two numbers out. But now, as time increases, because this first qubit is talking to everybody else, so you can imagine that the unitary dynamics can mix wave functions, so that qubit of information alpha 0 plus beta 1 no longer located at localized to the first qubit, and it kind of start to spread out. And now, so this one can ask a question. Okay, where's that information?
Exactly.
Yeah.
So, right on cue, I wanted to talk about quantum information scrambling.
Okay.
You also gave an example of the perfume bottle.
Yeah.
And another common example is when we mix cream in coffee, which people often give, where information is initially localized and then it spreads throughout the system until it becomes very hard to reconstruct it. So how close do you think is this analogy to what actually happens in a quantum system? And how do you define quantum information scrambling?
Yeah, so the way the way I define it is precisely what I just talked about. You start with a state that you are known at all other qubits in some known state, for example, in some reference state 0, and the first qubit is something you encode some information in the first qubit, and then you can ask, and of course because the dynamics in the unitary, you can always recover that information from the four-wave function. For example. You can, let's say you have some time-involved state, psi because it's unitary and you know the dynamics, so you can always apply U dagger to it to sort of reverse the time or rewind the time. Then after the same time, but backwards, the information is relocalized in the first qubit, and you can read it. So that's so that just means that the information is kind of scrambled to the entire system, because at a given time it's no longer at the first qubit. But also means that it's not leaked outside the system, and you can recover it eventually, in principle. But now, a more interesting question is, like, do we always need the four-wave function to recover the information?
Right.
Because imagine this. So let's say let's start to evolve the state. So the information is no longer in the first qubit, but kind of spread out a little bit, but our interaction is local. So it means that the information will not be able to jump far away in a short amount of time. It's kind of like the speed of light. Yeah. It's kind of bounded by some speed. Okay, here we call it a Lieber-Robertson bound, but this basically just means that the information cannot spread too far away at a short time. So this kind of defines a sort of a profile of the information. It's basically like when you pour your cream in the coffee, this sort of spread out. It's not like instantly feel the coffee, right? It's also like if you drop a drop of ink in water, it's also spread out. It's not like instantly.
Yeah.
So there it kind of means that at least for a short amount of time, you do not need the full 2 to the n wave function to recover it. And you just need a subset, right?
Right.
And this also means that in general, like if some error occurs, in the process, it may actually will not affect the information that you just encoded, because you do not need the full wave function to recover the information.
Right. And
yeah.
this can only happen in for a very short time. You only need a subset of the wave function.
Yeah, so that's actually very interesting. Yeah, so definitely for short time, you only need just its neighboring few qubits.
Right.
And then the question is now, let's say if we involve system for a long time. Okay, let's say it's just long time, just no matter how long you want. And in this late time limit, do we need the full system to recover the information or not?
That's the question.
Yeah,
Yes.
that's the question. I don't know if you have an intuition.
I see. So when
I mean, this is a question for you. Do you have an intuition?
It's a question for me. Yeah. Well, I think the answer is that. Well, I think from my point of view, if the information has spread out to enough degrees of freedom, well, in principle, you can apply a U dagger and sort of try to make all that information localized back into a subset or or in the most ideal case back to the first qubit.
Okay.
But I don't think it's, well, I mean, you if the system thermalizes, then you cannot do it, right?
Yes, turns out that so I mean, I guess that's maybe the intuition that most people have, but it turns out that this quantum mechanics doing something kind of more interesting.
Yes.
It's kind of like, it turns out that even in the late time, everything is more or less as long as the system is closed, it's still interdynamics. You do not need the entire 2 to the n qubits to recover the initial information.
I see.
It's you actually only need about half of it. So you need let's give some number. Let's say you encode you have your initial information is in 1 qubit, and let's say you have 20 other qubits. So you have 21 qubits, right?
Yeah.
And of course, initially, I mean, it's also, let's make simple. Let's think it's in a chain geometry, so so every side has 2 neighbors. And then of course, initially, as I said, information cannot spread very far, so you need just the first qubit that's maybe a couple neighbors. And that range will start to grow over time, because the information can spread more and more. So then you may think, okay, maybe eventually the information will spread out to the entire system, and I need the full 10. Did I say 10? Yeah, the full 11 qubits to recover the initial information. But turns out it's not. Turns out in the late time, I mean, given that the dynamics is sort of generic, you only need 6 qubits or 7 qubits. It's like half the systems plus a few qubits to recover the information.
And what is the intuition behind this half?
Yeah, so the half is sort of like let's see, so in the late time, because the dynamics is generic, and so eventually every qubit kind of are equivalent. And then from that we can argue that one cannot recover the information from smaller than half.
I see.
Because if you can, means that let's say you can because if you can, then you can recover it from this half, or I mean, let's say you can recover it from 1/3. So that means you can recover from this 1/3 and the other 1/3. So it means you can recover the information from two non-overlapping subsets. Then it means that you can sort of clone the information from two ends. That's not allowed. But I don't have a good intuition why it's like why it has to be 1/2, not like two thirds or like that. I don't know, but it just happen to be that way.
Yeah. I mean, one thing comes to mind is that because we're also bounded by the fact that any operator that we use to access that information should have some notion of locality, right? So with local operators, if the information has sort of scrambled across the system, it's hard to retrieve. But apparently, you're saying that we only need half. So I'm assuming that the support of that operator would also be closer to like the half size of the system. Is that?
Yeah. So basically, it just means that by half, it just means that you can just literally throw away the other half.
Right.
And you just do whatever you can. There's some generic operation you can do on the remaining half.
Yes.
And if you do it in the right way, you can correct the information. And I guess so this whole idea of this also related to the whole idea of quantum error correction.
Yes. Yeah.
Because if you really need the entire wave function to recover the information, it just means that any error to it will affect the information itself.
Yeah.
Well, if you need only half of them, means that the encoding is redundant. Means that you have some sort of allowance for some error to occur, while still be able to recover it.
Interesting. Okay, so I think in response to again taking like a historical route here, in response to Einstein, Podolsky, and Rosen's this seminal Einstein-Rosen bridge paper, this EPR paper. It was Schrödinger, if I believe correctly. He pointed out that entanglement is the characteristic feature of quantum mechanics. So for the viewers who are not familiar with what entanglement is, let's start by you telling us what is entanglement and how we can use entanglement also as a probe of many body dynamics.
Yeah, okay, good. Okay, very good. Yeah, entanglement, it's the EPR pair. Because I say this so often that I don't really remember the full name, but it's called an EPR pair, or maybe EPR.
Einstein, Podolsky, Rosen.
Okay, good. Yeah. So entanglement is a phenomenon. Means is that say we have two qubits that are entangled, in explanation, people usually put it in the EPR pair. It's like the standard wave function. EPR pair just means that the two qubits in a state, 0, 0 plus 1, 1, which just means that no matter what they do, they have the same state. And then if you measure one qubit and reveal it's 0, then it means the observer immediately knows that the other qubits are also in 0, no matter how far away they are. So in principle, let's say someone creates a pair of the EPR pair, hand the first spin to Alice and the second spin to Bob, and as Bob they travel to opposite direction, to the edge of the universe, so very far away. So and then Alice measures her qubit. Let's say 0, then she can immediately know that Bob's qubit is also in 0. So it's called entanglement. Basically, like it means how much information you can get from measure your own particles.
Right.
How much information you can get from about the other particle when you measure your own particles. And this is kind of counterintuitive because that seems suggesting some sort of way to break the speed of light. Because Alice and Bob, they can be super far away, but what Alice measures her qubit immediately affects Bob's qubit to force it to be the same state. And also that's also in many sci-fi books, people write this about using this as a mechanism for instantaneous communication, like breaking the speed of light. But this intuition itself is kind of wrong. That the entanglement itself does not break the speed of light. It's basically because you cannot. Even Alice knows Bob's has to be in the same state. She cannot communicate with Bob.
Right.
But yeah, entanglement is still a useful, very powerful resources for quantum mechanics systems. And yeah, as I said, people, the first step to characterize the dynamics is through local measurement, local observables. But these observables, they tend to thermalize, and in a very short time, it's basically in a time like about 1 over the characteristic energy of the system is like 1 over the coupling constant. So it's short time. But we also know that the unitary dynamics, its unitary means that it does not have really a sort of fixed state. Unless you start with eigenstate. But if you do not start with eigenstate, the state itself will in general evolve forever.
Right.
Then we have some tension here. So from your measurement, you only see, okay, everything kind of equilibrates, cools down. Opposed to a steady value for a short amount of time. But the state itself is still evolving.
Right.
So it must say that. But also local observable only represent a small set of the information of the full wave function. So it's not saying that something else of the wave function is still evolving independently and not captured by those local observable. So the question is, what's next thing to measure? Because we don't want to measure all the 2 to the n wave function amplitude. We want some sort of coarse-grained observables that are beyond all those local observable to measure. So what are that? So then the entanglement turns out to be a good thing or good quantity to use to track the dynamics over the time when the system thermalizes. And here, the entanglement, people usually use something called a bipartite entanglement. Basically means that you artificially cut the system into 2 halves, and track the entanglement between the left part and the right part as a function of time. So if you start with the plus state, means all zeros or all ones, the initial entanglement is 0. And as your time continues, as time increases, the left part starts to talk to the right part, and some entanglements start to build up. And you can kind of apply entanglement as a function of time, and see how fast it increases and when it reaches some steady values.
Right.
Yeah.
Right. Interesting.
So you talked about thermalization, and we will come back to thermalization in a bit. But before that, I want to talk about chaotic systems.
Okay.
So now, chaos has found its way in everyday language, but in physics, we mean something very particular. At least in classical physics.
Okay.
So how about you start by explaining what are chaotic systems, and what is the contrast between chaotic systems classically and quantum mechanically?
Yeah, so classically for chaos, it means that the sensitivity to the initial condition, right? So if you put the 2 bars in some billiard table and start with tiny different initial locations, and the trajectory of 2 bars, they initially track each other, but after some time they become completely different. So that's the sort of the standard understanding of chaos. It means the sensitivity to the initial condition, and it's very important for the weather forecast, for stock market, so on and so forth. Like for basically, it's there for any complex systems. But for quantum mechanics system, it's a little strange, and the people usually when you talk about chaos, they usually have different quantity in mind to measure chaos in quantum systems. So Yeah, I guess one can also like use this idea of the sensitivity to the initial condition in quantum systems, but now but in quantum systems you usually talk about the wave function. So you um so in that way, you're basically saying, okay, let's say we start with a one wave function involving time, and let's say and then we perturb it by a tiny bit, and start involving time, and one can ask, okay, how different they are in late as time increases, right? But if you do this the way, it turns out that the distance of between the two states they never change over time because they just basically just two vector overlap, and as time increases, the overlap is the same. So one cannot really use this as a definition of chaos in quantum systems. So that's so there's the attention here, and then okay. So then, what do we mean by chaos in quantum systems? Again, I mean different people using different definitions, and there's actually a paper called "The Web of Chaos." That's basically yeah, so sort of talk about different measures of chaos in quantum systems and how they relate to each other. I don't want to really go over, the whole sort of the whole literature on quantum chaos, and also I'm not an expert as well. To me, maybe I'll talk about mention one definition. It's one definition is basically ask how basically have a reference in quantum system, like what's the most chaotic systems, and then talk about how your quantum system is close to that reference. So that reference is basically a random matrix. A random matrix just means that okay, you have instead of physical system is more structured. You have a local interaction, so on and so forth. So you have a Hamiltonian, and it's local interaction. So a physical Hamiltonian is not a random Hermitian matrix.
Right.
Well, but you can say, okay, but can we compare it with the random matrix? Let's say you have a random Hermitian matrix, and then you have your physical Hamiltonian. You can say, okay, do they have the same properties? People use that.
And by properties, you mean eigenvalues?
I mean, not the eigenvalues, but more like of course, eigenvalue itself is the energy, does not mean too much. It's basically people compare how the levels, how the eigenlevels, they repel each other.
Yeah, okay.
That is it's called a level repulsion. And they use that as a way to define whether the system is chaotic. And there are some other ways, like the spectrum spectrum form factors, so on and so forth. And to me, I don't know. Maybe like for knowledge, if the different definition of chaos they point to the same thing. Then another sort of class of definition of chaos is sort of used through the semi-classical limit, like you make your system like large n, so quantum mechanics sort of approaches classical limit, and then in that classical limit we can use our normal definition of chaos that way. But the question there is that but this is only applied to semi-classical systems, not the arbitrary quantum many-body systems.
I see. Also, like with chaos, and you said that one definition that you really like, which is we have a reference that a random matrix, the level spacing of random matrix, look a certain way, and how close is this physical Hamiltonian to it. But we've also figured out, like over time, we figured out there are physical systems that appear to be chaotic. So my point is that chaos ends up showing in many scenarios. It seems very universal. It shows up when people are thinking about black holes, which are extensively studied from the gravity side, in field theories, and condensed matter systems. So do you have any intuition behind why chaos is sort of universal? Why are we finding these Hamiltonians look that describe physical systems, but also are sometimes closer to what random matrices look like.
Yeah, I guess the intuition is that you can kind of think about, structure is rare. And, let's imagine, let's say if you, shake, a bottle of bars like black and white, and they always tend to mix each other. So my intuition is always like the disorder is common. Order is rare, and in that sense, that whatever system you write down, or or you implement in the lab, has a high chance to be chaotic.
I see.
And the non-chaoticness need to be designed. So you need to sort of fine-tune some parameters, like or fine-tune some interactions, and for it to be non-chaotic.
I see. Yeah.
So it's kind of the typicality problem. Like whatever, I mean, there's in the zoo of systems, there's those few and not chaotic or more structured. But if you pick a random one, it's
most likely chaotic.
Yeah, it'll be most likely be chaotic. Yeah.
But I mean, the only problem I have with that, I mean, it's not a problem per se. I mean, I completely understand what you're trying to say. The only thing is that because something that is so abundantly available, because if you pull a system out of a hat, it's going to be most likely it's going to be chaotic.
Yeah.
In order to define something like that, we sort of need like a reference point and not like a standalone sort of definition. So that's kind of counterintuitive to me, but maybe it's just the way it is.
Yeah, I mean, so one always needs some sort of definition, say, how chaotic the system is. And that is more subtle, right? Because you need some sort of measurable or some sort of quantity to do that. And there's a few different definitions, but they are related. And but I just don't know whether they means the same thing.
I see.
So chaotic systems, like chaos and thermalization, are very closely knitted through eigenstate thermalization hypotheses.
Okay.
Which talks about how the system can look thermal, even though the underlying, even though it's unitary, right? Which is the case in quantum mechanics. So how do we understand this statement of saying that unitary, even though the system is unitary, it can thermalize? How do we understand this?
Yeah. So again. So as I said, like symbolization, it means local observables. So it means that, so it's like about those quantities we measure locally, like single spin or a few spin measurement. So from that, it can go to a steady value, while because it does not represent the full state. So basically, like from the 2 to n vector, you can get to those observables, but you cannot reconstruct the 2 to n state from those observables. So that still leaves rooms for extra dynamics beyond that local observables. And so in that sense, so it's not really against any rule of unitarity, because the state self can still evolve while system looks thermal. So that's why it's kind of, so it seems like some sort of hierarchy of information that can be sort of constructed from the 2 to the n. You can start from local measurement, then maybe setting non-local measurement, then maybe full non-local measurement. I don't know. It seems to me there's some sort of some structure of information there that one can build.
So in principle, we can reconstruct the information.
I mean, of course. So if you be able to measure every sort of wave function amplitude, then it just means the full state tomography. That means that you can just read out what the state is.
Right.
But that requires a lot of effort.
Yeah. And ETH is also sort of tied with the emergence of classicality and statistical mechanics. So how do you think about this idea? again, I really like the fact that you said there's like this hierarchy of information that we can extract from the wave function.
Okay.
Is that how you think about emergence of statistical mechanics that ETH sort of conjectures?
Yeah. So there's also this idea of emergence of a statistical mechanic, because after all, quantum system, if it's closed, it's just closed. I mean, but in many time it appears similar to Gibbs ensemble, and so it's also this kind of similar idea. From the ETH just means that the eigenstate looks thermal.
Right.
Means that the local state of your full state looks like a Gibbs density matrix, but there still leaves rooms for some arbitrariness if we talk about the full wave function.
I see.
So basically, if in a small energy window, so yeah, the interesting about quantum mechanics systems that you have is in terms of eigenstate, you have to the n of them. But your energy window, but your energy, the energy span of your eigenvalue is proportional to n.
Right.
So which means that if your n very big, you are really packing like exponential many state in a linear in n window. So if given small energy window, you have tons of states there.
Yeah.
While ETH suggests that for that within a small window, those states should all look same or similar.
Yeah.
But we also know those states, they should also not to each other. So it just means that the simulations sort of account for a small part of the full wave function.
Right. So another thing I find very fascinating, and it is partly because I do not completely understand, is are these quantum scars,
Okay.
which are these special states that somehow avoid thermalization in an otherwise chaotic system. So how do you explain that?
Yeah, so scar is it's an interesting topic. It's in the classical setting, scar just means that if you have some sort of chaos systems, but if you really be carefully placing the ball at a particular location, start with a particular velocity, it can sort of stay in a closed orbit and not really explore the entire phase space. And I mean, the classical example would be a three-body problem, which the three balls that are attracted by gravity force. This is chaotic, means for arbitrary initial setting or random initial setting, those balls can be whatever. I mean, everywhere. But if you place in a very precise setting, they can form all different interesting closed orbital patterns.
Right.
And and in quantum mechanics, scar just means that there's a few ways to say what a scar is. One is in terms of the eigenstate. It just means that from an eigenstate point of view, it just means that maybe more the majority of eigenstate looks like typical, like thermal. Okay, but there's just a few of them looks different. It looks atypical. They can have their own properties, and if you plot some property of the eigenstate as a function of the energy, and as I said, from ETH, those properties should only depend on its energy. So you'll get a mostly smoother curve, but you'll see a few outliers, and those outliers are the atypical states that they should basically do not follow the general trend, and those atypical states can have some sort of effect on dynamics, even though there are only a few of them out of the 2 to the n number of eigenstates. For example, we from a simulation we expect all the observable they should equilibrate or approach to a steady value after a short time. But for a system with scars, some observable can oscillate for a long time, or at least a much longer time. But those scars are there because the physical Hamiltonian, as I said, is more structured. So there's no reason to expect to be completely random or chaotic. And there's a few, and then to me, it's not surprising that there's a few outliers and lead to interesting properties. To me, it's not violating anything, and it's interesting. It means that we can, it's. I mean, if everything is random, it means it's sort of less interesting.
How is this different from many body localization?
Okay, yeah, many body localization means that you when you include a strong disorder to your systems, that every eigenstate, the majority of eigenstate do not look like what you expect from ETH.
Yeah.
So while scars, it means that the scar system can be perfectly clean, don't need disorder. It in fact it appears in some most well studied quantum systems without disorder. And also for scars, it's not the majority of eigenstate. The majority of eigenstates, they are still fine. They look normal. They look thermalized and obey ETH, but it's just a few outliers. While in many body localized systems, like most of states are not thermal. And in fact, people talking about anti-scars, which means that you start with the many body systems, many body localized systems where most of states are not thermal, but you have a few outliers that actually are thermal. So these are called, people call these anti-scars.
I see. So like again, just to understand this correctly, the outliers that you say, so what's happening is that somehow ergodicity is being suppressed. Is that right? Is that the right way to understand it?
I don't know about how you define ergodicity here, but it just means that for those, for example, like most of the state, they have energy. So from energy, you can infer the temperature that it would be in the Gibbs ensemble, and then from that you can estimate what the local observable should be look like. So which is basically the thermal values. But when you measure those scar states, it will be significantly deviate from that thermal value. Yeah, and also means that if you so I don't really know how to define ergodicity here, because quantum mechanics itself is, because it's unitary, so it's not ergodic. I mean, just in principle, because when you start with a state involving time, it's not going to be able to explore the entire Hilbert space.
Right. Yeah. Great. So let's sort of zoom out a little.
Okay.
These days we know there's like a growing overlap between different communities of physics. For example, condensed matter, quantum information, high energy.
Yeah.
We have models like the SYK model that have a holographic description and so on. So tell us, why do you think these communities have started talking to each other now, and what do you think are some individual and combined goals? What are some of the reasons behind these communities have started talking to each other? What are some open problems individually and also like in this collective combined sort of collaboration?
Yeah, right. So I mean, I can only speak for myself, because to me, like what's interesting is like those community or those different fields, they have a general theme, which is like the many body plus quantum mechanics, or quantum many body physics. So in condensed matter, like historically really studies I don't know, solids,
Right.
like materials, and AMO group, they sort of study single atoms. Quantum I mean high energy studies, quantum field theory, so on and so forth. But they all have a sort of a problem. I mean, a difficulty, like what happens if you have a lot of degrees of freedom together, and that's precisely the region, the quantum of quantum many body physics, So then one can ask the questions that instead of sort of ask about a particular sort of systems, whether it's solid state or cold atom or quantum field theory, more about a question like what can generically happen given given constraint of quantum mechanics and the many body systems. And it turns out there's some sort of universal behavior there, regardless, independent of which platform you are looking at. And that makes sense. So we can sort of say something more universal, and that's why people in different community they talk to each other, and also they along the way they have invented their own tools, and those tools can be helpful for other community as well. Yeah.
Interesting. Very interesting.
Right.
Yep.
Now, shifting gears a bit, and I want to talk about something which is a recurring theme in quantum mechanics, which is measurement. And I mean, even though measurement sounds like a very basic thing, especially in physics, it is something that we have not agreed upon what we define as measurement in quantum mechanics. So how do you think about measurement, and how do you think it ties to the whole quantum foundations picture?
Oh, that's a kind of somewhat vague questions. I don't know. I mean, to me, like measurement in quantum mechanics just means Bohr rule.
Okay.
That you measure something that collapse the wave function to whatever the outcome is with given probability.
Simple.
Yes, it's simple. But to extend, okay, why is it happening? That I don't know.
Do you find yourself thinking about it?
Yeah, no, I do find myself thinking about it. I mean, the way I think about it is like, well, it's just my own sort of thought. I mean, I think I totally agree with the Bohr rule. You know, but why it's happening, I don't know. I think I kind of want to think of myself as whoever the observer. Whoever the observer is a part of the global systems. That when one measures a qubit, it becomes entangled with the qubit.
Right, yeah.
So then, so basically, like I perceive the qubit to be zero. That just means that it's kind of I form an APR pair with that qubit. So if the qubit is zero, I'm also in the zero state. If qubit is one, I'm also in the one state. So I can only perceive the outcome because I'm tied to the outcome, in some way. So sometimes I view myself, out of part of the quantum systems.
That's very Everettian, actually. You being tied to that's like the many words.
Yeah, so it's kind of like the many words interpretation that there can. So when I observe a qubit, I can write the wave function as qubit 0 minus 0 plus qubit 1.
Exactly.
I'm 1, and so.
Yeah, I see. Interesting. Very interesting. And another term, I think we should sort of like circle back to this because I think we did not discuss it. Again, also something that has, various definitions. We've been using locality very freely. So what does locality mean in terms of observables in a quantum system, in a physical system?
Yeah.
And how do you think about it?
Yeah, locality just means that it's like, I think locality is also like a generic principle of like quantum body systems, because if we allow arbitrary, 2 to the n times 2 to the n matrix or 2 to the n times 2 to the n operations, then it's kind of unphysical. So physically it means that a qubit can only talk to some other qubits through some particular interactions. I mean, there are long-range systems. Means that qubits can talk to some qubits far away, but I still think it's as local because it's not like the entire system. It's still structured. Imagine this, right? So let's say if we allow arbitrary interaction between an arbitrary pair of qubits, we have mostly n choose 2 pairs. It's n times n minus 1 or 2.
Yeah.
So that's still a small number. While if we allow arbitrary interactions, then it's 2 to the m times 2 to the n matrix. It's a completely different story. So locality just means that you have this, somewhat geometry local interactions. And that was sort of imposed a sort of a strong constraint on what the system can be.
Right. And and people also confuse this with quantum mechanics having some non-local features. So what's the confusion there?
Yeah. So here, I guess the local here means different things. Like when people say it's okay, quantum mechanics is non-local, it's mostly they mean by entanglement, which means that you measure, as I said, you measure one party can affect the other party no matter how far away they are. So in this sense, it is non-local. But when we say locality in many body systems, it means like the range of the interactions between the qubits. So it's not the entanglement is non-local, but I guess it just means two different concepts. But it's happen people using the same word, so that's why it can be confusing.
Right. And there's also a debate. I mean, a debate and like confusion about. So whenever in the high energy community, whenever people are studying field theories and so on, what they come across is an infinite dimensional Hilbert space. But in many body systems, we have finite dimensional Hilbert space. So what's going on? Which one is it?
So I'm a kinetic math series, so I always prefer a finite dimensional Hilbert space because it's more rigorous, because you have a vector space and it's linear algebra and then everything is okay, what should I say? So everything is predictable, or at least in principle. But now when you get to the point you have infinite dimension of Hilbert space, it becomes to me, because I'm not really an expert in field theory. It just seems it's a bit hard to keep with. Of course, that also brings some convenience that you can do a large N technique, saddle point approximation, so on and so forth. To me, it's kind of hard to understand what's going on in that limit.
Right.
So I always, I always prefer systems with finite dimension, at least to start with.
Yeah.
Maybe in the end, I can take D to the D local dimension to infinite in the end. But I always want to have something concrete to start with.
Fair enough.
Yeah, but it's maybe just my it's because I don't really understand the quantum field theory.
Fair enough.
So a very hot topic recently in these years, and something you also work in, is AI for science.
Okay.
So what do you think, like, where exactly or how efficiently has AI been for physics? Like, where is it genuinely helpful?
Yeah. Okay. Yeah. Very interesting topic. AI for science. So, it's people use AI for physics in many different ways. From help doing coding. Or self become a tool in physics study. For example, like a way people usually use AI, at least in my field, is that the AI just means a function. It has some input, it gets some output. So one can use this as a sort of, and the wave function is also a function that takes the input, which is your qubit configuration, and output number, which is the waveform amplitude. So then one can say, okay, let's using AI function as the wave function. And then the wave function has some tuning parameters. And just like the AI model has some parameter to train, and then one can say, okay, how well the AI wave function can mimic the real wave function. And then this is a common way use of AI model in physics. Because in physics, there's a long history using something called the variational wave function. It's just a trial wave function, contains a few parameters that you can tune, try to lower the energy or something to reach the target wave function. And now the AI wave function is not that different, but it has, much more parameters, so it has more expressive powers, and we have the modern training toolkit to train it more efficiently. So the one can hope using those AI wave function to sort of reach the get closer to the true ground state, so on and so forth. So that's one use.
That's a very interesting way to call it, AI wave function.
Yeah.
I mean, all people call it, I mean, I use AI wave function because, the
Similarity.
yeah, but people, the jargon is a neural network.
Yeah.
state.
Yeah.
There's some other use of AI, for say image recognitions, like cause we accumulate tons of experiment data, and then it's hard to sort of process by human, and then the AI can sort of try to extract some pattern from those data. Well, but I'm a theorist, so I don't really do experiments. So the other way I use AI a lot for is like help me coding, So before I need to really hand code, let's say, the code to simulate the hybrid model or something. Right?
Yeah.
Now using AI, it can now write the code for me to simulate the hybrid model or something, and then I can check. And now they become so good that most of the time it gets correct.
Yeah. So is it like a tool that you sort of like, it's almost like an assistant that is always working with you on a certain problem?
Right. So it's like it's like assistants that I can just ask, hey, do this, do that for me, so I can sort of give some low level work to AI, so I can focus on think about new ideas. Yeah.
So what work are you careful with giving to like, let's say, a large language model? You said you're okay with some low level work, do this, do that.
Yeah,
But
for them.
when are you most cautious?
Yeah, like the wave function, should we trust AI completely?
Oh yeah. So let's say I ask before large language model, I will say, hey, I need to simulate this Hamiltonian. Now let's sit down and code in open Jupyter notebook, code in Python.
Yeah.
Now the workflow is, hey, ask AI, hey, can you do this for me? And the AI write the code in a couple minutes. Well, I need to do it for like an hour.
Right.
Then I spend next 10 minutes to review the code to see if it makes sense. So it saves me some time.
Interesting. Yeah. Okay, so you've spent a lot of time in academia. How do you think it has changed in the last decade or so? No, and not just like with the onset of AI tools, of course, that has caused a humongous amount of change, but also just like the mindset, funding opportunities. I know that like there are communities. I mean, we did talk about that communities are not talking to each other, but at also a coarse grained level, we see that there are silos forming that actually don't talk to each other, and there's a question about, is fundamental science stuck or not? Do you have any strong opinions about any of these?
No, I mean, I don't have a really strong opinion about this. I mean, I think at least for my research, for my own research, they haven't been similar. Okay, of course, it's affected by AI tools somewhat, but to me, I mean, the way I do research now, like compared to research like 10 years ago, is kind of similar.
Oh, okay.
I mean, I don't know. But of course, different people may have a different opinion, and also it depends on the field.
Right.
Yeah. I don't know. It's maybe because I haven't traveled that much recently.
Fair enough.
Yeah.
Fair enough.
But obviously, because of AI, the work that you as a graduate student were doing is now different in how your graduate students are working. So what advice do you have for them when it comes to using AI, or just any, like the way they're using new tools? Because when you did your PhD, you did not have these tools and you had to do everything by hand.
Yeah, no, I always think new tools are good. Are good, right? So you're always using new tools. In fact, I'm also interested in like making some new tools for my research and so on and so forth. But regarding to AI, I don't know. I mean, I would say do not fully trust AI for your research, because it's not always correct. Another thing that sometimes it will pretend it's correct, and it's very hard to sort of understand to check. So you should not trust the AIs. Let's say for example, let's say you are the guy that gave you a research questions, and I mean it's fine, and I totally think it's a good idea just to ask AI for that. But you should not trust the result until you verify yourself.
Nice.
Yeah, I
Yeah.
mean,
That
I
makes
think
sense.
AI's answer gave you some like intuition, some direction to explore. They may mention some tools you never heard of, and you can like check okay if it makes sense. But but you should always be the student should always be the person to sort of verify the
Everything.
result. Yeah. I mean,
That
otherwise,
makes sense.
yeah, it's also, I mean, even AI makes everything perfect. It's still, it means this is a process of learning, right? Yeah.
Exactly.
yeah.
Yeah. All right. So we're sort of in the final part
Okay.
of the whole thing. So tell us about your journey as a physicist. We're at the Nomads podcast, extremely curious about
Mhm.
different researchers, how they started doing physics, what sparked your interest and so on. So
Yeah.
as far as you can go back, what made you interested in physics?
Yeah, I don't know. It's kind of start random. Yeah, I guess so. Well, my physics journey, I mean, I would say it started in my college. I mean, when I choose physics as my major in college, right? So I guess the moment I decided to do physics is basically when I applied for physics major in college. And why I applied for physics, because I mean it's kind of random because I was pretty good at the physics and the math in high school. So so I need to pick one for my major. So I said okay, I don't know, let's pick a physics.
Okay.
And since then I was being the physics major. I spent 4 years in physics major in undergraduate, then 6 more years in grad school, then postdoc, then faculty here. So yeah, I don't know. It's kind of a random decision in the beginning.
I see.
Yeah.
I see. Do you remember anything that perhaps have sparked your interest, or it was just you knew that you were good at physics and
Yeah, no, I think I always been so kind of wondering how nature works. I guess that's most people's reason why they like physics, because it could give you some sense of how opens the door for you to understand the universe and the internal working mechanism of the universe, even though now it still don't understand everything, but it's at least open door for you, so we can learn more about it. Yeah.
Okay. And how do you, on a daily basis, keep that motivation alive?
That's hard. Yeah, so because research means that most of the time you stuck, right?
Yeah.
So I always recommend some sort of side hobby to do. When something is stuck, you switch to the side hobby.
Okay. What are some of your hobbies?
Yeah, no. Well, now now I'm like well, a few things. So first of all, now I have a 2 years old at home, so I really don't really have much time for a personal hobby. Then after beyond that, I do vibe coding. Vibe coding just means that use AI to code it for you. So as I said, I in academic writing, use LaTeX or something. So I was trying to explore, ask AI to write me something different, just to understand how LaTeX works. Are there any alternatives? Yeah, that's what I've been doing.
Interesting. Yeah. Do you have any advice for up and coming grad students and young researchers?
Yeah, I don't know. I guess it's because now with AI that's shaping the whole academic field, I was just just keep doing research and enjoy the ride, because you don't know how where the future can take you to.
Yeah. That's
Because
great.
now, it's very unpredictable, but the most important thing is to enjoy doing research in the field. Yeah.
That's Great. Thank you, Shenglong, for being on the Nomads podcast.
Yeah, no problem. Yeah.
We had
Thank
fun.
you.